Section 10.3.RA-1. Based on interviews with 105 SARS patients, researchers found that the mean incubation period was 5.6 days, with a standard deviation of 13.5 days. Based on this information, construct a 95% confidence interval for the mean incubation period of the SARS virus, and then interpret the interval. Okay, so first let's write down the given information. Okay, we first need to identify, okay, what is the mean of this particular question? We can see here that the mean incubation period was 5.6 days. Okay, and then we also need to figure out, okay, what is the standard deviation? We can see here the standard deviation is 13.5. Okay, and then what is the sample size? Well, the sample size is 105 patients. So n is equal to 105. Okay, so now we're going to use the t distribution to create a 95% confidence interval based on the statistics from this sample. And note that the sample size must be large, which means that n must be greater than or equal to 30, or the population must be normally distributed. We can see there that n is equal to 105, therefore it is greater than the 30. Okay, so now we know that a 1 minus alpha 100% confidence interval for the population mean is given by the following. The lower bound is taking the sample mean minus the t critical value times the sample standard deviation over the square root of n, and the upper bound is the same, only thing that we have the plus here. Okay, where the critical value, t critical value, is the critical value with n minus 1 degrees of freedom. All right, so let's go ahead and first find this information to find the critical value. Okay, so for the chart, okay, the chart that we're going to look at tells us the area in the right tail of the distribution. Okay, so let's go ahead and take a look at this. We know that alpha is equal to 1 minus 95%, which gives us 5%. Which then gives us a decimal of 0.05. Okay, and then we need to take alpha and then we need to divide that by 2. So therefore, if we take 0.05 and then divide that by 2, well, that's going to give us the 0.025. So recall that we're looking for the area to the right. So what that means here is that in this critical value that's located wherever it is, okay, we know that this area represents 0.025, and then this part on the left side is 0.975. Okay, so we know that the area in the right tail is equal to 0.025. Okay, and so that is the first part that we need to know. And then the second part is, okay, what is the degrees of freedom? So recall that the degrees of freedom is equal to n minus 1. And so we know that the sample size is 105, and then we're going to subtract 1 to get 104. Okay, so now that we have the area in the right tail, which is 0.025, and we know that the degrees of freedom is 104, okay, now we can determine what is the critical value that we need. Okay, so we're going to use our chart. Now, if we take a look at 104, okay, we know that in the top part, this is the degrees of freedom here on the left. So the column is the degrees of freedom, and then the top is the area in the right tail. We can see here that the area in the right tail is given by 0.025. So here is that part. And then we also see that the the value of 100 is down here. And we don't see 104, so when you're using a chart, you're going to pick the one that's closest to that number, which is 100. So in this case here, if we scroll to the right here, and then go all the way down from here, we're going to see that it's going to give us this value here. So we end up getting a critical value of 1.984. So therefore, this is equal to 1.984. Okay, so now what we're going to do is we're going to find the lower bound, and then we're going to find the upper bound. So the lower bound again is taking the mean and subtracting the critical value and then multiply it by the standard deviation over the square root of the sample size. So in this case here, we know the following. Go ahead and move this down just a little bit to make a little bit more room here. Okay, so we know that our mean is 5.6, and then we're going to subtract the critical value of 1.984 times the standard deviation of 13.5. And then we're going to divide that by the square root of the sample size, which is the square root of 105. So let's take a look and find out what the approximation is of the lower bound. Okay, so using our calculator here, okay, so we're going to use this first. So we're going to take negative, this is 1.984 times 13.5, and then we're going to divide that by the square root of 105, and then we're going to add the 5.6. So we get the following number. And so we're going to round that to 2 decimal places. So that gives us 2.99. Okay, now we're going to go with the upper bound. And the upper bound, again, is taking the sample mean plus the critical value times the sample standard deviation over the square root of the sample size. So we have 5.6 plus 1.984 times 13.5 divided by the square root of 105. And then the upper bound is going to be the following. So let's go ahead and do that. So let's come up here. And then we're going to go ahead and then get rid of the negative sign here. We're going to hit enter. So we're going to take 1.984 times 13.5. We're going to divide that by the square root of 105. And then we're going to add the 5.6. So let's take a look at this result. And so we're going to round this to 2 decimal places, which is 8.21. So now what we want to do is go back to the question. It says interpret the interval. So let's go ahead and interpret this interval. So we're going to say the following. We can see therefore the lower bound is 2.99 days and the upper bound is 8.21 days. So there is 95% confidence that the mean incubation period lies between 2.99 and 8.21 days.